Kia ora, Year 11 and 12. Here are two more questions from last year's calculus paper. So the first of these is an excellence question, and it's kind of a classic kinematics problem. So I'm going to go quite slowly through that one. And then the second one, 2D, is a merit question, but it's one where we have to draw the function where we're given the gradient function. So here they go. So this is the kinematics question, and it's about Adam who is operating his drone. So when you've got these problems, you have to read them really carefully to pick out the key information. So the drone's moving in a straight line, and t seconds after passing a tree, we're given a function that gives acceleration. So the acceleration function is this one here. 2 seconds after the drone passed the tree, its velocity was 20 meters per second, and we have to find how far was the drone from the tree when its velocity was 20 meters per second. So those two link up. The key thing in here is that time is defined as how many seconds after passing a tree, right? So when we're asked about the stuff down here, it's all defined in the time since the drone passed the tree. Now, a quick refresher on how kinematics problems work. If you're watching this video as soon as I've made it and you're in my level 2 class this year, we actually haven't done this yet, but you'll get the idea pretty quickly. So the first thing we start with is the idea of displacement, which is roughly how far something has gone. So this is displacement. And we move from there to the idea of velocity, which you can think of roughly as speed. So to get from here to here, we differentiate. And then to get from velocity to acceleration, we differentiate again. So all kinematics questions basically come down to this setup. Now to go backwards, we anti-differentiate. In other words, we work backwards. And when we do that, we have to work out what we call the constant of integration. The other notation that you'll see me using that some teachers don't use in level 2, but I do, is this thing here. So for example, if I had, let's do a really silly one, if I had x to the power of 17 plus x to the power of 12, and I want to anti-differentiate it, I write it like this. And my answer would be this, would be 1/18 of x to the power of 18 plus 1/13 times x to the power of 13 plus this mysterious plus c. Okay, now what we're doing here is we're saying, well, I'm starting here and I want to go up a power because I'm undoing differentiation, right? So I'm working backwards. And you can check that when you differentiate this function, you'll end up back here. And the plus c is something that we have to figure out. So that's not how I'm going to teach it to you in class. We'll go more slowly than that, but that's the idea that you're going to need here. Because in this question, we're starting at the bottom of the chain. We're starting with acceleration, and we need to end up back up here, figuring out how far the drone had gone. So there'll be quite a bit of anti-differentiation in this problem. Right, so the first thing we're going to do is we've got acceleration and we're going to get a function for velocity. And we know that v of 2 is equal to 20, right? And we know that because this says 2 seconds after the drone passed the tree, that's what its velocity was, it was 20. So let's get into it down here. So we'll start by writing out a of t is equal to 6 minus 12t. So v of t is this, right? It's the antiderivative of the acceleration function. That gives me 6t minus 6t squared plus c. Now, to pin down what that plus c is, I use the fact that after 2 seconds, or 2 seconds after the passing the tree, the velocity was 20. So we can write this down, and now we substitute in 2 here, and we get 20 is equal to 6 2's minus 6 times 2 squared plus c. Cleaning that up gives me 20 equals 12 minus 24 plus c. So 20 plus 12 is equal to c. C is equal to 32. So lots of writing, but it's not conceptually that difficult, right? We're finding an expression for the velocity at any time after we've passed that tree. So 6t, 6t minus 6t squared plus 32. So that's good. Now let's go back and look at what we were asked to find. Right, we were asked to find how far was the drone from the tree when its velocity was this. In other words, at t equals 2. So we're going to now go up the last step, and we've got velocity, and we're going to go backwards to get displacement. So s of t is the antiderivative of velocity. So we'll put in our velocity function, and we go backwards on this. So let's see what we get. Well, I'll have 3t squared, right, this power is going up 1, minus something t cubed, that will be 2t cubed, plus 32t plus c. Now, what's the plus c here? Well, we know that t equals time after passing tree. So at t equals 0, how far has it gone from the tree? Well, it hasn't gone anywhere, right? So at t equals 0, it's at the tree. Okay, sorry about the background noise. I've got some extra kids in the house today. So we can put in, here's s of t. Now we know that s of t is just equal to 3t squared minus 2t cubed plus 32t. Right, so we've just about finished. We've got an expression for how far the drone has gone at any time. We're going to substitute in 2. So we get s of 2 is equal to 3 times 2 squared minus 2 times 2 cubed plus 32 times 2. That works out to be 12 minus 16 plus 64. And when you add all of that up, you get 60 meters. So after 2 seconds, so 2 seconds after passing the tree, the drone has travelled 60 meters. Okay, so if you get all of that figured out, that's an excellence question. Lots of practice at those in the theta book. There are some really good ones in there, and there's quite a bit in the Walker book as well. So now I'm going to look at 2D, which is only a merit question, but for some of you is going to feel, I think, harder than the kinematics ones. Okay, so if you've been watching these in order, you'll know that question 2A in the paper was to go from the function, which I think was an upside down parabola, to drawing the gradient function, right? And so we knew there that if we had a parabola as the function, the gradient function would be linear. I'm just looking if I've got that right. I think I have. And this question is the reverse of that one, which makes it a little bit harder, but not that much harder. So in this case, we're given the gradient function. So the gradient function is a quadratic. So f dash of x has got this shape. We have to figure out what function it came from. But we know that if we differentiate a cubic, we get a quadratic. So there are two kinds of cubic. There's a negative cubic, or a cubic with a negative x cubed coefficient, and that has this pattern, that shape pattern. And then we have a cubic with a positive coefficient, which looks like that. For example, if we had x cubed plus 2x, right, this would be a positive cubic, and it would differentiate to give me f dash of x is equal to 3x squared plus 2, right? So we know that we'd get that shape. If we had a negative cubic, for example, say we had, f of x, start again. Suppose I had f of x is equal to negative 2x cubed plus 9, then f dash of x, the gradient function, would be negative 6x squared. So the negative cubic gives me an upside down parabola. The positive cubic gives me an up the right way parabola. So we know where we're heading with this question if we're good at identifying that we're starting with a positive quadratic, right? So it's going to be coming from a positive cubic. So what can I say to start us off? Well, the first thing we do is that we know that the turning points in that positive cubic are going to be where the gradient is 0. So let's look on here for where the gradient is 0. So here's the first place, and here's the second place. And we know that this one is going to be the maximum, right? Because my gradient up here is positive. and then my gradient becomes negative for all of this bit. So for all of that yellow part, the function is going to have a negative gradient. And for the green part, the function is going to have a positive gradient. But we need one more thing to anchor us, and that's this information here. That the graph of the function, y equals f of x, passes through 0 and 3. So we're going to put that point on first of all. So down here, we're going to mark on 0, 3. And then we know that at this crossing point here, so this is at x equals negative 2, we've got to have a maximum. And we know that at positive 4, we've got to have a minimum. So we can put on these values here. So this is at negative 2 and at negative 4. 1, 2, 3, 4. These are going to be special points. Now I don't mean that that is a point there, I just mean to mark the negative 2 and the negative 4. So at negative 2 we've got a maximum. So we can chuck it in anywhere as long as it's above this point here, right? So we might make it here. And at negative 4 we're going to have a minimum. Now we could draw it here, we could draw it down here. It doesn't really matter. So let's now try to draw that cubic. I'm going to make this up. There. Okay, so that's one example of what we're looking for. That won't be exactly right, okay? To get it exactly right, what we could do is we could figure out exactly what f dash of x is. Okay, so we could get an equation for this, and then we could anti-differentiate. I'm going to just finish off the way that you need to do it, and then I'll come back to how we can get it exactly right. So looking down here, what have we got from that top graph? Well, we're given the information about 0, 3 being on the curve, so we have to have that on our curve. And we've figured out that the shape is going to be a cubic. And we're going to have a maximum here at negative 2. Right? So we know that's going to be a maximum because that's where the gradient is 0. And it's coming from a positive gradient up here and changing into a negative gradient. And that we can see happening down here because we've got a positive gradient here and then we've got a negative gradient here. And we take the same approach over here at 4. So we can see back up here at x equals 4, the gradient down here is positive. Sorry, the gradient down here is negative and the gradient up here is positive. So you can see a positive gradient here as we leave the minimum and a negative gradient here heading into it. Right? But the exact values that you put on don't really matter. But let's go back and suppose that we do want to work out what this equation is. I'm going to erase all of this stuff. Nice being able to do that. Let's write down a functional form here for this cubic, for this quadratic. Well, we know we've got f dash of x is equal to some scale factor a times x plus 2 times x minus 4. And we could substitute in a rough value to get this figured out if we wanted to. Okay, so we could get a value for a and then expand that out, and then we could integrate it to get back to get f of x exactly. And you could chuck that into your graphics calculator to have a wee look at what the graph looked like, but it will look roughly like the thing that I've drawn down here. Okay, so I've done that very laboriously and slowly because these questions are ones that level 2 students find really confusing, but they come up all the time. And the reason that they're in the exams all the time is that they make you get a really good understanding for what a gradient function is, right? So up here, this is showing you the slope at any point for this curve down here. Right, so going backwards, you can see here the slope is 0, and up here the slope is 0. So the two graphs link up. Thanks for watching. I'll do question 2e soon.